Hello and welcome to this ATAR Note Head Start lecture. My name is Dash. We'll talk about me in a second, but welcome to this ATAR Notes lecture. This is Math Methods. A little bit first about what ATAR Notes is. I'm very lucky to be with ATAR Notes. I myself was a student. You'd be shocked. I graduated in 2023. The school wasn't so different then. I didn't know how to study. I didn't know what to study. The idea of study resources seemed quite alien to me. But as you go up in school, it kind of gets harder. And I realized that I didn't have the tools available to me. Got involved with some pre-ATAR note stuff, and then I saw and had recommended to me a lot of their which now I've done the kind of study guides and topic tests. And at the end of the day, for math especially, but even chemistry, um, the amount of uh, practice questions you do is probably the best predictor of exam success and learning from the mistakes. Obviously, you can't just do questions without ramifications. But that's kind of how I got involved with ATAR notes. ATAR notes are great. They've got so much stuff. Study notes. I did 800 Plus, which was like a free, or it was all, sorry, I should say it's all included, where you'll get access to all the resources online, which was just so convenient. That's what I did in 2023. There's online lectures, online Q&A, videos as well, plenty new coming out, newsletters. ATAR Calculator, I use that thing all the time to try and work out what subjects were going to get me where I needed to articles, and there's more. There's even an AI tutor now, which is pretty cool. Kind of draws upon what past students like myself have written. Internet Plus, what I was talking about before, and here is that AI answer bot, which actually draws upon the books which are written like tutors like myself and sometimes by me. And um, so it's kind of accurate. It's using real information. I okay. So we're in January. Now, what are we actually going to do today? We're pretty well going to do Unit 3. Now, I know that some of it will be kind of consolidation, and that's totally fine. Um, there'll be a big bulk that will be new, and we are going to round out Unit 3, which is exactly how it's going to work. We're going to get up to pretty much the level of the I1, I2, sorry. So to avoid confusion, I'll just say your first exam. Right. Obviously, different schools can do it differently, so just bear that in mind. All right, so my name is Dash. I'm a third year medical student at JCU in Cairns. I graduated in 2023. Now, my rationale when I was choosing subject, I chose specialist and kind of high scaling subjects. My rationale was I want to be a med student, and for every one person who gets in, there's 16 people who didn't, who applied and were eligible. So it is pretty competitive. You have to be pretty locked in, as I'm sure you all are. And if you're not, well, guess what? You can definitely improve heaps. I feel like that's true pretty well everyone. I guess what defines me, love to run. I've done marathons and ultra marathons. Really been getting into the gym over the past year or two and traveling. I'm actually not in Australia at the moment. I am in Italy for a study abroad program, and that's one of the awesome things about uni is that you have all of these great ways to spend your government debt. You can spend it overseas if you want. And I think that is totally awesome. So you can put it on your hex loan, which is just great. So I'm in Italy for 2 weeks, and they don't book the flights. So like when the course is over, I'm going to go to Eastern Europe and Poland and all these places you probably wouldn't have heard of, and I hadn't heard of at your age probably either. Um, yeah. Okay. So stuff we're going to talk about today. Firstly, we're going to look at logs and exponentials, then trig functions as well. So obviously now in year 12, we're mostly talking about calculus. Calculus and probability are the main two things. So differentiation and integration. Um, and we're also going to talk about how to solve logs and exponentials and discrete random variables right at the end, which was actually in unit 4 back in my day, but it's the same content. This is overall. I think I will make this pretty clear. If you see a resource that predates 2026, so anything 2025 through to 2020, it's pretty well going to be pretty close. Okay. It's definitely going to be closer than if you were to do something from the Victorian syllabus. Obviously, preference things that are more recent. Some things have changed. QCE might change its preference for certain things, but the objectives are about 90% the same. So 90% is pretty good. So you guys have a lot more study resources available because the syllabus has just been around that much longer than it was for me. And that's a massive advantage because practice questions are the best way to learn. They're not supposed to be feel good, but they're the best. Okay. We are going to start off now with a bit of consolidation about exponentials and logs. This slide might be a bit unfamiliar. That's totally fine. It's mostly demonstrative, and you can have a plan, you calculate it if you want. We're not going to bother today. So this is in one of the objectives. Let's try and find the limit of this equation here with technology. So kind of going down in increments, maybe by power of 10, 0.1, 0.01, 0.01, as h is approaching 0. Uh, and it gives us the gradient of the equation y equals a to the power of x, which you'll recognize because that's an exponential. And it gives us that gradient at x equals 0. Now, different values of a, so a being from the equation, so a to the power of h, a to the power of x, um, is going to give different gradients. We use technology because it's not a proof. We can't really do anything fancy math-wise. If you're a specialist brain, you're trying to think of it, but you can't. And for most values of a, this limit is not going to be 1. But there is one value of a, so remembering a is just a constant. It can be anything between negative infinity and positive infinity. So we're just cycling through them, and there is exactly one number out of those infinities where the limit is 1. And that value is e. E is Euler's number. I think it's like 2.8 something, whatever. You don't need to know. I don't know. You don't need to know. But it's a special number. It's named after a mathematician. Um, and we essentially, your logs now are going to be taken over by it because it makes the math a lot easier. Now, if you try and differentiate a log which doesn't have a base of e, so you know how it's like log 10x or whatever, log 10(2), we replace the 10 with e because it makes differentiation a lot easier. Now, if it wasn't e, you have to like change the base. You have to physically change the base, and that's the quickest way to do e, and then go around it like that. So it's kind of a pain. So don't be surprised that after I've told you this, that all the logs you're going to see from now on are going to be ln, natural log. So the special thing about this e is if a number a, so in this equation here was b, the limit is going to be 1. So it's a pretty special and unique point. And then here we have the proof. So e to the power of h minus 1 divided by h equals 1, where h is approaching 0. Okay. So E is special. The rate of change when x equals 0 is the same as the limit at x equals 1. Well, I don't really need you to understand this. Go into it if you want, but the important thing is that if we differentiate an exponential with the base e, that is going to give us an exponential with the base. Oh, sorry, e to the power of x. It's the exact same. You're not tripping. The differential of e to the power of x is e to the power of x. This is on your formula sheet. Do not stress. Now, it's not inverse chain rule, but chain rule by pattern refers to if we had like e to the power of 2x. So there's a function up there technically. 2x is not x. 2x is the function of x. So technically we would do chain rule being that we'd find the derivative of the thing inside the functions, the derivative of 2x, which is 2. And then we go, okay, well, what's the derivative of e to the power of u? And derivative of e to the power of u is just e to the power of u, or e2x. Then using chain rule, it would be u dash times v dash, which is 2 times e to the power of 2x. Basically, what happens is we take the derivative of what's up here and we pull it out the front. So if this was 2x, the 2 come to the front. If it was x squared, 2x would come to the front. And this rule is in your data booklet, so that's a win. Um, but you do need to be able to appreciate when to use it, how to use it. Okay, log graph feature. So this would be a bit revisionary, but then again, different schools do things differently. And guess what? You might just forget. And I remember coming into year 12, and honestly, I'm pretty sure I forgot like the exact values for trig, and you just forget little things, and it comes back, but it's pretty scary at the start. Okay, so first thing we need to appreciate is that logs are actually the opposite of exponential. So if you can kind of follow with me here, and I'm going to grab the y and x axis and I'm going to shift it like this. Okay, so I'm essentially swapping it 90 degrees. And what shape would that red line, which is stuck to the axis, be? If I swap it like this, it's now going to be an exponential. Okay, I have a log and now it's an exponential. So they are the opposite of each other, which makes it quite interesting because if we have a log and an exponential opposing each other in an equation, they actually cancel out. So if we had e to the power of ln x, it would equal x. Why? Because e and ln are the exact opposite. So whatever ln does, e does the opposite. Now, ln is simply log e, okay? So whenever you see ln, the n means natural. So ln is just log e. So this would be e to the power of log e x. And the log e and the e are going to cancel out. The opposite is also true. So if we had the natural log of e to the power of x, that would equal x. So the ln and the e once again cancel out. Now, this is more of a specialist thing previously, but it is in your syllabus. So I would know it. It could potentially not commonly, but be a mark involved with a complex familiar or unfamiliar, especially in the external. They love to pull this kind of stuff. And you won't be able to solve it if you don't recognize, oh, don't those cancel out because they're the opposite? Okay, so here are the features of a log graph. So log graph, this is the base case, typically looks like this. Now there's a couple of interesting features. The y-intercept is the d-value, um, and yeah, and the vertical asymptote is, so vertical meaning coming down would be this one here. See how it's like getting very close to -1 here, but not quite. So that's because c equals 1. And remember that because it's in brackets, it's kind of like math is playing a trick on you and it's the opposite. So even though this is reading as y equals, because of the values I've got here, y equals ln x plus 1 plus plus 1. The plus 1 would make you think maybe it's going to the right, but because it's in brackets, it actually goes the opposite way. So it's 1 to the left, which is why the asymptote is 1 to the left. Now, if we think about why this asymptote exists, it's because we can't have anything 0 or less in the brackets of a log. So um, if we kind of sub in that, okay, x plus 1 equals 0, if we rearrange for what value of x would make that true, i.e. that it was a 0 in there, which is not true, can't be true, and is therefore an asymptote, it would be x equals -1. Um, Now, a lot of people might ask, oh yeah, but it looks like there's an asymptote with x equals 4 or y equals 4. Not true. Although it's kind of plateaued, quote unquote, it's going to keep going, and technically it doesn't have an asymptote. Okay, with these a and b values, they are going to kind of reflect it. So obviously, if we make a negative, that's kind of attached to the y, like it's pretty close to the y. So I think about it as it's therefore going to flip across the y-axis, which kind of makes sense because it just means that all the y values are going to be swapped because it's close to the y. Whereas the b1 is going to swap it across the x-axis because it's attached to the x. Sorry, I said it around the wrong way. it's going to swap the y values from positive to negative if it's attached to the y. So the a is attached to the y, meaning that it's going to be swapped this way across the x-axis, so the opposite. Whereas the one attached to the x means that all the x values are going to be swapped. So actually, it's going to swap the other way, so across the y-axis. Okay. Log and exponential laws. You're probably thinking, why on earth am I still learning this? I hate this. I hate math. Well, these are actually pretty relevant, and fortunately, you've seen them before. So, unlike many things um, you will study, you've actually seen this before, and it's time to really lock it in because these laws are going to start getting important. Not this slide, but like the slide after, when I'm going to start showing you how to solve some particularly difficult problems. Okay. Now, the first one here, we've actually already talked about. So if we've got like a log and an exponential, they're actually going to cancel out. Um, so the ln and the e are just going to cancel out, so that's just x, and the same with the e to the power of ln. Okay. All right, log laws. These are also on your formula sheet, so it's important you can recognize them though. If I've got ln a, so obviously because it's a natural log, they've both got the same base, so we don't even need to worry about that. But if I've got ln a plus ln b, logs are kind of like how I think about it is logs are like in their own different dimension. So if I'm plusing two logs, I'm going to multiply the content. If I'm minusing two logs, I'm going to divide the content. Okay. So Um, being able to recognize this is really important because as I'm going to kind of talk about later, a lot of the time in math, the really smart kid, potentially it's you, it will be you after this lecture, but what they do is it's not necessarily some kind of explicit, okay, it's not like 4D chess where they're seeing 8 moves in the future. No, 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 no. It's kind of a vibes-based thing. And I say this as someone who scored 97 out of 100 in methods for year 12. It's kind of vibe space, okay? You kind of do what makes sense and can kind of change it. You simplify where possible. And knowing these log laws means that when you're stuck and you're like, ah, crap, what do I do? I don't know where I'm going with this. If you just kind of go, oh, well, I mean, I can see that I can simplify it. You don't have to understand the big picture and go, okay, but yeah, how is that going to help me to solve this problem? Just do it. So where's half a mark? You know, chase half marks, don't chase full marks. And then if you build up enough half marks, maybe you will get full marks. That's kind of my philosophy. Um, so yeah, these are really helpful. Being able to recognize this, practice, practice, practice. Do not neglect this topic. All right. Then we have, if we've got like to the power of something in the brackets, doesn't matter what the power is or anything like that, we can bring it to the front. Now, this can be particularly useful if it was like lne, because the base e, or like let's say it was lne squared, the base e is the same as what's in the bracket, e squared. But we just got to bring the power, which is 2, to the front, and then log e is going to be 1, because if the base matches what's in the bracket, it just equals 1. As you'll see in countless examples if you go into the textbook. A couple of exponential rules as well, and if you want to know, these rules are actually perfectly mirrored. It's just their opposite because of logs versus exponentials, but they've got the same underlying math. All right, so exponential rules, if we've got e to the power of a times e to the power of b, we add the powers. So same base, we add the powers. Once again, this is an index law. It's kind of like in a different dimension, and so it just, instead of multiplying the powers together, we add them. All right. Then if we divide by, we minus, and if we've got like actually this is quite interesting. I'm not sure if I've seen this one. If we've got e to the power of a, all to the power of k, I think I understand it now. Yeah. Okay, this reads confusingly, but I'm going to try and explain it simply. So here's in here is e to the power of a, and then on the outside is to the power of k. So this isn't like e to the power of a and then there's a k on top. This is like the e to the power of a sandwich in brackets, then there's a k here. What we do is we multiply. So the bracket means that we just multiply the two powers. Okay, solving exponentials a lot. This comes up a lot. This is going to come up on your first exam, and it's also going to come up on your external exam. Look, this is consolidation. I really shouldn't be spending too much time here because we want to get to other stuff in this class. We probably touched on it before. I'm going to be honest. Like, you might have slacked off towards the end of last year. You might be thinking, oh, yeah, but year 12, the externals are at the end. I'm going to give it a while to warm up. No, 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 no. Hit the ground from day one. I don't care if you do half an hour of homework a day or in a week, but start doing it. Start making it, that you are doing it. Because all of these practice questions, and guess what? If you do three of the practice questions and it's the easy ones and you nail it, fantastic, good for you. Yeah, don't do 20 more of them, but definitely do go to the hard questions and test yourself against them. Because there's a lot of nuance to this topic and there's a lot of nuance in math. And, if you're someone who's quite smart that will do one or two questions and be like, oh yeah, I got it. You might still barely pass because you didn't go into the hard question, which is worth about half of the marks anyway. So hit the ground running, and you definitely want to practice these ones. And I can't teach them all, but here are some kind of guiding rules. So I find that it can help to kind of switch between logs and exponentials. So if you're a bit stuck trying to solve one of these, if you swap it from an exponential to log, that can help. Also, if there's a mix of exponentials and log, you definitely want to like unify that and put it all in log. So you kind of use, once again, vibes to figure that out. And you got lots to swap it between exponentials and logs. It's not rocket science. You got it on your formula sheet. Here's log form. Here's exponential form. Which one goes where is on the formula sheet. So big win, big win. All right. If two things look like they can be put together, do it. It's almost never coincidence if things can be simplified. Like, it sounds stupid, but it matters by design. Like, your teacher is writing these questions, and quite often there's not that many ways to go about it. I know if you try and do maths through ChatGPT, it'll probably make up math, but in reality, there's not many, especially what you're taught in school, there's not that many ways to go about a question. So if something seems like it could work, chances are your own insecurity is honestly throwing you down. Run with it. Right. Example. So solve e to the power of 3x minus 2 equals 7. Now, I can't solve this. I don't know if you can, but once again, going back to our first rule there, we are going to swap between logs and exponentials. So we are going to swap this into an alternate form, log form. So notably, the base, which is e, is also going to be the base in the log. So ln, natural log e. So whenever you see an e exponential with Euler's number, it's going to translate to a natural log. Those two are intertwined. So the only thing that swaps is the thing in the brackets of the log, which is 7, gets swapped for the thing in the brackets with the e, and then we swap it in log and exponential form. Then we rearrange for x because that's what we're trying to find, and this would be a perfectly acceptable answer. Sometimes it's not pretty. If you have a calculator, you can make it a decimal, you can make it 2 decimal points and it'll feel a bit better maybe, but it isn't important that it's pretty. What's important is that it's right. Okay. Now, this can get a little bit harder. By a little bit, this is like a complex familiar type question. Pretty common though. And to be honest, as complex familiars go, there's hard ones and there's easy ones. For this topic, if you really nail it down, there's not that many variations, and you probably will smash it because there's not too many applications. But for integration, there's heaps of applications, and it can get quite hairy. Um, so honestly, we'll lock it in, and it will serve you quite well. So let's talk about these. So this is still solving logs and exponentials. Um, Now, simplifying a log, you can. It's pretty easy. So the reason I'm showing you the example of how we use quadratics, it's called algebraic substitution. So sometimes we use quadratics to solve hard quadratics. Sorry, hard exponentials and logs. Now, um, you have used algebraic substitution for exponentials, but when it's a logarithm, if you just follow the basic logic of, okay, I'm just going to simplify it, see what happens, you're actually going to come out on top. So if I had like log x plus 3 plus log x plus 2 equals 0, and bear, give me some patience because it's in my head, but okay, we've got two logs and, oh, sorry, I should say that they're two natural logs. Oh, they've got the same base. Brilliant. Now we can, because they're plots, we multiply the content. So log or log-e or ln x plus 3 times x plus 2, which would be x squared plus 6x plus 6. Don't worry, I don't care if you can do that in your head. You don't have to. Um, but the important thing is that we've now got log ln x squared plus 6x. Now I've lost my train of thought. No, log x squared plus 5x plus 6. Obviously, you write this down if you want. Equals, you don't have to, equals 0. Now, what we can do is kind of go, okay, this does starting to look like a quadratic. Now, the problem though is that it's ln quadratic equals 0. We have to get it out of the log because you only have a finite number of skills in math, and one of those skills is completing the square or the cross method, ACB method or quadratic formula. You've definitely heard of some of them. And so what we need to do, or dots, and so what we need to do is we need to get it in full quadratic form. So we put it in exponential form, which is going to be um, e to the power of 0 equals x squared plus 5x plus 6. E to the power of 0, anything to the power of 0 is just 1. It's going to be 1 equals x squared plus 5x plus 6. Take the 1 across to the other side because we want it to be 0. Is going to be 0 equals x squared plus 5x plus 6. Now we just use the cross square or whatever, completing the square to find two possible values of x, and there we solve it. And I can do it in my head. Means it can't be that bad. I'm no genius, that's for sure. Um, so, okay, that's the easier one. Now, the hard part is when it's an exponential, and I'll tell you why in just a second. Okay, so why would it be harder with an exponential? Well, the thing is, you might get something like this. Solve e to the power of 2x minus 5e to the power of x plus 6 equals 0. What the hell? How do I solve that? Because you can't simplify that. I'll give it away. You can't simplify that right off the bat. There's no, the logs, we can kind of use that fuzzy logic where we're like, okay, those can simplify, so I'm just going to do that. I'm just going to see what happens. We actually can't do that, which makes it just that little bit harder, doesn't it? Yeah, sure does. So what we do is actually quite clever. We use u or big X or theta or gamma or whatever symbol you want to use, and you let e to the power of x equal u. Now, this is not, we're not about to do any differentiation or any fancy math. The only reason we do this is because it allows us to visualize a quadratic. Now, what do I mean by that? Well, let's go back to one of our index laws, because if we're letting e to the power of x equal u, then the equation here the minus 5e to the power of x is just going to be minus 5u. The plus 6 is still plus 6. But what about the e to the power of 2x? How is that going to work? Well, let me tell you something about that. Remember that index law where it was like, if we've got like e to the power of x and it's to the power of something, we would just pull the power in, like it becomes multiplying. We can actually do the opposite here. We've already got it inside the e to the power of 2x. We can actually put it outside of the bracket so that it's e to the power of x all squared. Okay, why is this important? Well, that means that now we've got e to the power of x to the power of 2. What was e to the power of x? U. Or u to the power of 2, or u squared. And here we see the simplification. U squared minus 5u plus 6 equals 0. Now we can use completing the square or cross method or quadratic formula, ACB method. These are all year 10 concepts. Chances are one or two of these probably, you might not know them at all, and you don't have to because you do a very similar process that's the exact same. But I mean, if you don't know completing the square as a pure method student, then I wouldn't be too worried. Chances are you won't need to know it unless you're taking like an A plus and you want to shore up every base. Quadratic formula is probably worth a look at again. If you don't know any of them, then please go back to your year 10 and 11 notes, mostly year 10. Okay. Essentially, we use that factorize. Now, the reason that we're factorizing is because we want to ultimately use null factor law. Now, null factor law states that the product of two things equaling 0 means that one or two of the products must equal 0. Therefore, u minus 3 must equal 0 or u minus 2. Rearrange both and we get the u equals 3 and u equals 2. Now, you're going to make this mistake at some stage and you'll go, okay, well, I got my final answer. Yay, good for me. Well, not quite, because u actually equals e to the power of x. And what did we want to solve for? We wanted to solve for x. So we now have e to the power of x equals 3. Oh no, how do I solve that? Guess what? If it's sometimes it's written in the wrong form, so it's currently in exponential form. If we swap it over to log form by rearranging them, sometimes we get a good answer. As is the case here, it immediately equals x equals ln 3. Yes, big win. It's immediately good. And then the same for the other one. Cool. Okay, so it's not that bad. Okay. Yes, you're gonna have to practice it. And yes, it is a complex familiar question. But you want to be aiming to get these. I know, and I really hate hearing this from students like, oh no, I'm only gonna do the easy ones. I really need to just focus on getting the easy ones. And it's like if you if that's your mentality, we need more practice. And if it's the day before the exam and you haven't done any study, then yeah, sure. Maybe it's about just learning the basics, and yeah, you're gonna take a lot of marks on the hard ones. But for me, especially, I would make so many mistakes throughout my exams on simple things that I needed to be like accessing all the marks. So, I always strive to learn those hard ones. You don't want to preclude yourself because even for the super smart student, like I got 48 out of 50 on my external exam. For me, was I immediately understanding questions? No. Am I a test grandmaster? No. So it doesn't really help. You kind of go based off vibes, and when you're doing the practice, it's supposed to be hard. Okay, the harder you train for a marathon, the easier the marathon is. If you don't train for a marathon, you're gonna have a pretty crap day. So it's the same thing here. If you're just doing the easy questions and what feels comfortable, you're not learning. It's like doing 3 bicep curls at 5 kilos and never going up. You're not really gonna like you're gonna build up to that strength and then you're gonna go no further. It's about progressive overload. Okay, let's start talking about differentiation. So you're going to be doing a lot of derivatives. You've already done a lot of derivatives. You're going to do a whole heap more. If you're a specialist, you're going to do even more than that. But fortunately, we got the data booklet, and in methods, the data booklet is really, really super duper helpful. So that's a big win. We let's be appreciative of that. So the derivative of ln x, so the natural log of x, is 1 over x. Now, what is ln x? Remember, ln x is log ex, so the natural log of x. Essentially, and it sounds weird, doesn't it? Because it sounds like a natural log in the forest. Like, be so for real. What is that? But um, it's natural because of that random proof that I showed you at the start. You don't need to know it. I don't know it well. Um, it's more for appreciation, so that you can apply it. Now, importantly, there's no derivative for log e or log 10x. You would have to change the base. You'd have to physically change the base to ln x. Very hard, very annoying. Okay. Now, another thing with this is we can use chain rule or chain rule by pattern if there's something inside the X. So similarly before, I forget what it was for, what we were talking about, but if we've got so 1 over X, if it was like 1 over 2X, um, we can kind of use this by pattern rule to bring, because what are we going to do? If we're finding the derivative, we're going to do this chain rule by pattern. So you chain rules in the data booklet, and we'll talk about that later. But by pattern is okay, well, every single time I do the whole chain rule, it just always just brings the derivative of what's inside the function. So inside the ln x, so inside this bracket here, it always just brings it to the front. Therefore, you kind of could learn it by pattern, so pattern recognition. Now, the interesting thing about those derivatives, if it was ln 10x, for example, and I did the derivative of that, I would pull the 10 to the front, so the 10 would therefore be on the top. It would be 10x, so it'd be 10 divided by 10x, which is 1 over x. So it's actually quite funky, the derivative of ln x, because it actually cancels itself out. It's quite bizarre. You're not crazy. That's how it's supposed to work. Um, so don't double check your answer if you get that. Mm. Before I go on to the next slide, I wanted to take a little bit of a brief break. We're now um, about 40 minutes in, and we've got 66, 67 slides, and we will motor through the latter half because it's mostly probability. But I wanted to um, take a bit of a quick break because we've been flying through things to talk about sheet maps. Now, at Eighth Notes, we mostly deal with content creation, and I'm in both Eighth Notes and Shootmax, but Shootmax is the tutoring and the tutoring branch. Many of you have probably had tutors from your hometown online. Shootmax runs online tutoring for high school students. Uh, I am a tutor. I've had many, many students now. I've probably had 30 students all up now, and lots of other tutors like me. Very smart, very um, kind of open, and you do have to have people skills to pass an interview and show that you can be a good tutor. So it's very welcoming because we've been students before and we know that this stuff is done hard when you get there, and I'm not going to kind of lord it over you that I'm doing med and it's so hard. Yeah, it is, but high school's done hard too. It's really hard to do these subjects. Like I'm not going to hide it from you. Just because you did well doesn't mean it was like easy. It's not easy for anyone. Even the person who looks like they never study and they do so well. It's not because they're naturally smart. It's because they just study at home, and it's not that deep. You gotta. It's called the the Solomon effect, where I think we underestimate ourselves and overestimate the competition. You're not at some natural disadvantage. You can do this, okay? You do have the potential. You have to have that self-belief. That is the base from which you work. I've seen students go from failing chemistry in year 11 to getting 85% in year 12. And I can't claim credit for that because of their hard work. And tutors can't help. That is true. Uh, so online weekly sessions, you can go fortnightly if you wish, um, by tutors all across. So you kind of have this advantage because it's online that you're not limited to tutors within your local area and you have to travel and stuff like this. It's from the comfort of your own bedroom and it's the best tutors from across Queensland, which is the advantage. Anyway, um, break over. We are going to get back to content. Now, that basic formula here isn't the only one that we need to know. And you guys are actually pretty lucky, as you guys are in the new syllabus. There's quite a few more formulas that we didn't have. But what that inevitably means is that they're going to test you on them. Whereas before, it was kind of like shock horror if they tested you on a formula that, no one knew. So you're going to be tested across a wider range of things, but at least they're on the formula sheet. No guarantee that you'll even know it's there in an exam and you'll probably just freak out, but it is there. So if you had that basic inkling in your brain, like, oh no, I don't know how to solve this. Well, I know that there's a bunch of stuff that I barely know in the formula sheet, so how about I have a bit of a read? You get a sense. Now, we're going to look at a very special example of this in 2023. Now, if anyone was paying attention, they would know that 2023 was when I graduated. So this was the external exam that I sat in my year, and it's had a bit of a doozy on it. All the teachers of that year kind of posted in their Facebook chat that like that was the hardest exam our students have ever done. Whether that's true or not, I don't know. It definitely was harder. Um, Now, there was a question where you needed to solve an integral and you had to disentangle this formula, but the problem was, unlike for you guys, this formula wasn't on the formula sheet. We actually had to, you had to have memorized it from somewhere. It's not on the syllabus, it's not really anywhere. And so it's oof, kind of rough. Now, for specialist students, I didn't memorize this formula either, but for specialist students, we could kind of cheat and use this other method called integration by substitution. Because if you do specialist, you'll immediately go, oh, yeah, well, of course, because there's but we can do a U sub because because we're using it against, look, we've got the derivative on top of the other one. So, of course, it's going to work. And it wasn't even the last question. So, this was a very hard question. I only knew one math student who genuinely got it right, and kudos to her. Now, the important step, which, like, just because of formula doesn't mean you're going to get it right. Like, I'm not going to, like, a lot of past students might say, well, they've got all the formulas and they've got all the, like, even in chemistry, you've got the pathways. Oh, they've got all of them. Therefore, it's so much easier for them. It's not fair. Well, no, because there's no guarantee that you're going to recognize it. Um, and they're going to ask more of these hard niche questions because you got the information there. Now, the good thing is that for you guys, the skill becomes not memorizing a bunch of stuff, but more so being able to apply and use information given in the formula sheet. Which is why, if you're in a bit of a pickle, always just go to the formula sheet. How much is it going to cost you? 20 seconds to skim over it? Like, it's not going to cost you anything. You may as well. Okay. So in terms of reading this, it basically says the derivative of ln x, not ln x, but ln function of x. So if we had like x squared in here or um, something else, something else, sine x, I don't know. It's going to equal the derivative divided by the derivative thing in the brackets divided by f of x. This isn't rocket science. You could do chain rule to figure this out. This is just basic chain rule. But where it became rocket science was when we had to integrate it. Okay, so let's have a look at this example. Question 16. So typically methods external exams have about 19 or 20 questions. So this is towards the back of the paper, but it's not the hardest question. There's going to be three other harder questions. So you're still expecting to get some marks here, even if you're only aiming for a B. Um, you don't want to be leaving this question blank. You know what I mean? Okay, so particle is moving in a straight line. Its velocity in meters per second. The particle is given by this expression for the velocity. T greater than or greater or equal to 0, where t is time seconds after moving from its initial condition. The initial position of the particle is 6 meters from the origin. We're going to focus on part A. Use calculus methods to determine an equation for the position of the particle from the origin at any time t. Now, a couple of concepts here. I'm going to skip ahead a little bit because methods is very integrated, so it's hard. Your external questions will kind of rely on interwoven topics. The first topic is that we have displacement, which is like, oh, I'm just moving through space, and then velocity is how fast I'm moving. So it'll be like meters per second. In 1 second, you move 10 meters. Great. And then acceleration is talking about like how much your velocity is changing. So if you're accelerating, that means your speed or your velocity is, if you use the accelerator in your car, the speed is going to go up. Okay. The displacement is obviously always changing, but the acceleration determines whether the speed is going to go up or down and how much in meters per second squared. Now, the position is also known as the displacement. So we want to turn this velocity equation into a displacement equation. Now, the velocity is the derivative of the displacement. Now, derivatives are the opposite of integral. Therefore, if we differentiated displacement to get to here, how are we going to put it back to displacement? We're going to integrate it. Okay, great. We set it up, and here's 1 mark already. The displacement equals the integral of 20 sine 2t divided by 6 minus 5 cos 2t. Now, the tricky part is that integral, because let me tell you, it is very nasty. And guess what? We're going to have to use that formula from before. Now, how are we going to use it? Well, look, cos and sine. Sine is the derivative of cos. So if we find the derivative, and we're going to have to muddle with it a little bit, but that's okay. The derivative of negative 5, 6 minus negative 5 cos 2t, derivative of 6 is 0, derivative of negative 5 cos 2t is going to be negative 10 sine 2t, which pretty well perfectly matches the top. And as you'll see in a bit, I'm not going to try explaining it. That is what we're going to use, because before we have this formula that basically says, because so the directionality is quite tough for students. I appreciate that. So we're currently going left to right. So the differential of this equals this. But what if we had this and we wanted to go back? We would then have to integrate this, give us ln f of x. Okay. Now let's see the formula in action. So here's the official answer. Now I've added this in. So first of all, we state that position is given by the integral of the velocity. And just by doing that, we already get 1 mark. So that's very nice. I mean, oh no, actually you do need to take out the 2. So the reason we take out the 2 is because, as I was saying before, what we've recognized is that it loosely follows this rule, right? Not perfectly, but that's fine. We're going to deal with that, where we've got the derivative divided by the function. So the derivative of cos is sine, and remember that 6 is going to disappear, so we don't even need to worry about that. And the derivative of negative 5 cos 2t is going to be, because the derivative of cos is negative sign, and then by pattern rule, with a derivative, we bring the 2 to the front. So 2 times negative 5 times negative 1, because it swaps to sign, and in doing so it becomes a negative. It's going to make it 10 cos 2t. Now, what does that mean? Well, that means that we need the derivative to be on the top. The derivative is 10 sine 2t. So we need to turn this gray one here into this black one. How do we do that? We take out the 2, which is pretty easy to do because integrals are like non-communicative. It low-key doesn't matter um, what we do to an integral. Like we can pull stuff out from it so long as we don't modify the equation itself. Like the ratio doesn't matter. So we're allowed to multiply what's inside the integral, do whatever, as long as we don't change any of the t's or any of the functions. So we're allowed to divide out the 2 because 2 times 10 is 20. So we haven't done anything, really. So we just pull it out to the front there. Cool. Perfect. Now we apply the formula. So we let ft, or f of x if you want, so that represents down here on the bottom, equal the thing on the bottom. So 6 minus 5 cos 2t. Okay, cool. We can now rewrite this whole thing as 2 times f dash t, i.e. the derivative of the thing on the bottom, which we've gone to all this painstaking effort to make sure that exactly matches, and we recognize that, and yep, good, we're all good. Okay, so we can therefore rewrite this as 2 times integral of f dash t divided by ft. Whoa, and then we jump to equals to ln ft. How have we done that? Well, this is now going back to what we're actually doing here. We've got this thing on the right here, okay, which is the derivative of ln f of x. Now, if I want to turn the thing on the right here into the thing on the left, I have to do the opposite thing. So because we're going the other way, we're not differentiating, we're going to integrate. So I'm going to integrate this thing here, which is what I'm doing, and that's going to give me ln f of x. Sorry, that might not have made sense. Essentially, another way I can explain it is um, we've gotten, no, I mean, that kind of, yeah, that makes perfect sense because we're already integrating that. Um, um, and then, like, in terms of, you're probably wondering why there's a d, like, if you're thinking, okay, let's rearrange this so that it's integral of this equals ln f of x with no d to the dx, which is like the derivative of this. If we integrate both sides, we're going to cancel out the d divided by dx. And because what we do on one side, we have to do the other, that means there's going to be an integral here left over. This is called integration by recognition, I think. Yes, it is. And it's something that you actually have to do in methods. And this is actually an example of it. So it's kind of by recognition, meaning if we've got the end product of a derivative, we can integrate it and put it back to the original. So we can integrate this result of the derivative to go back to the original. Okay, that kind of makes sense. Because they're opposite, they're yin and yang. Now, we'll see a cool graphic later. Therefore, if we've got the integral of this, it's going to shove it back the other way and turn it into ln f of x, which is what we have here. Then we actually sub in what ft is, which is going to be 6 minus 5 cos 2t, and then remember that plus c. So c is just a constant. We'll talk about that a little bit later, and that is always, always, always going to be there. Okay. And then we sub in the initial condition, and that is the initial position, i.e. when time equals 0 equals 6, and we solve for c to give us the final equation. Oh, okay. That is our first topic. So I'm going to have a drink of water, take a mental deep breath. I know it says consolidation. Chances are, it's been like 2 months since you've looked at this. You've probably forgotten a lot, and that's totally fine. I really don't blame you. Um, but you do need to know it again, which is why, the next time you see it, maybe not now, but maybe do some practice questions. Do the textbook work. There's a reason for that. Don't do all of it, but do the bits that you don't know. Do it until you're not getting it wrong, and don't do just infinite practice for no reason. You'll burn yourself out. But do a couple of examples till you get it right, and then move on to the hard questions. Right. Trigonometric differentiation. These ones are pretty fun. Sine and cos are. I don't even know the proof of this. It's in the 8 notes book, so you can actually look at it if you want. For not the 8 notes book, I should say, but the uh, uh, it's totally escaping what they are. What the specific name. It'll come back to me. I'll remind you. But the derivative of sine x is cos x. The derivative of cos x is negative sine x. And we have these chain rules by pattern. You can tell I'm just snipping pull this straight out of the formula sheet. Now that's great because we didn't have these ones on the right. So we would have to memorize the rules. And some of my friends didn't actually memorize it. And they would have to do chain rule to solve simple differentiation. So um, essentially the same thing. We take the derivative of whatever is inside of the cos x and bring it to the front. We find the derivative of whatever in the sine x, or whatever's in the brackets of the trig, and we bring it to the front. That's the only thing it is. So if it was sine 2x, we would bring the 2 to the front, such as multiplying. Okay? And yeah, we call them by pattern chain rule because you're using pattern recognition to solve something that is chain. So for example, derivative of cos 2x equals 2 sine 2x. The thing in the brackets remains the same, and then we just bring the thing in the thing in the brackets to the front. Okay. Here are a bunch of other differentiation rules. You don't need to know them, but you need to know how to use them. So, clutch factor is decreased in year 12 because if you've never seen something before, it doesn't matter if you've got a um, super awesome formula sheet. It's not going to help. So let's start with the basics. We've already done derivative e to the x. That's just e to the x. The chain rule for that, once again, we just bring the thing inside the function e to the x. So if this was e to the power of 2x, we'd bring the 2 to the front. If it was e to the power of x squared, we would bring 2x to the front. F dash x represents the derivative of f of x, which is a function of x. The derivative of ln x is 1 over x. And here we have the derivative of f of x, which is f dash x divided by f of x. And guess what? That's what we used to solve that problem. Okay? Which is in a slightly different context using by patterns. So that's pretty cool, hey? Now, as I mentioned before, if it was like ln 2x and we find the derivative of that, it would be 2 divided by 2x or 1 over x. So sometimes it cancels out and it can seem like you've done something wrong, but you haven't. That's just the math and how it works. We've already done these, so the two trigs, so we bring the 2 out the front, we bring the a value or the f of x, essentially the derivative of whatever's inside the brackets, we bring it to the front. Oh, okay. Complex differentiation rules. Yes, you still need to know them, and you should have definitely done them by now. But if you've forgotten them once again, that's not something I'm worried about. You'll pick it up, but maybe try and learn it this time. So chain rule is where we've got something inside something else. So a function of x inside of a function of x. So for example, sine x squared. X squared is its own function, but it's inside of a function of x, which is sine. So we've kind of got like this interlocking chain, one could say. Now, one thing I found particularly useful as a student was kind of the substitution of these. So knowing what to say is u and what to say is v. So if we've got y equals sine x squared, I would let u equal the thing that's in the function, which is what it's saying here. So if y equals a function of u, then u is the little thing that is inside the function, and v is the f of u, so the overall thing. And dy dx is just the derivative. And I've kind of translated this for you because it can be difficult to understand the dy's and stuff. Um, so the rule you have to memorize is v dash times u dash. So the derivative of the thing in there times the derivative of the whole thing, just considering it. So I always set it up like, oh, if we had find the derivative of sine x squared, let u equal x squared, y dash, or the derivative of u, sorry, u dash, and the derivative of u is going to be 2x. V equals sine u. The derivative of v dash, is going to be cos u. Then you multiply v dash times u dash, so 2x times cos u is cos x squared. Final answer 2x times cos x squared. I find that these red ones, although it's not necessarily you can see them very well and translate it, it's worth memorizing. Um, and you can kind of pick out which one is which based off what they kind of look like. Product rule. So product rule is what it sounds like. If we've got the product of two things, i.e. one thing times another, it is going to equal uv dash plus vu dash. So once again, let one of the products equal u, let the other product equal v, so u times v, and then we kind of alternate which one we differentiate. But I always do like the let u equal this, u dash equals this, let v equal this, v dash equals this before I actually start plugging into the equation because I need to work out what so that I can just draw from it. I'll show you what I mean in a second. Quotient rule, you honestly won't use that much. I don't know why they don't test it a lot, but essentially how it works is quotient is divide by. So if we've got a function divided by another function, thing on top we call u, thing on the bottom we call v. Formula is vu dash minus uv dash divided by v squared. Okay. Right, and here's an example. Solve the derivative of ln sine 2x. Oh my gosh, that's so hard. Why would I do something like this? This is totally within your scope. I would argue that this is a very easy complex familiar. You just need to practice. It will not be that hard once you've practiced. Okay. First thing we do is let u equal sine 2x. Now, why have I done that first? Why have I chosen that substitution for u? The reason is because okay, so ln sine 2x, we've obviously using chain rule. How do I know that? Because interlocking chains, we've got a function inside of another function, okay? Chain inside another chain. Sine 2x is the function inside of the ln part, okay? So we're gonna let u equal sine 2x. The derivative of sine 2x, we have to use the divide pattern here, but that's totally chill because you're gonna be so cool with that once you've practiced it. Derivative of sine is cos, and then we just bring the 2 to the front. Okay, so it's 2 cos 2x. Easy. Too easy. All right. The second part is we now deal with the whole thing. We let v equal ln u. V dash equals 1 over u. Okay, that's pretty easy. That's pretty simple. Now, I always do that first, so then I can just very cleanly substitute it into whatever rule I'm using. So chain rule is u dash times v dash. Once again, you do have to kind of memorize that or otherwise learn how to read derivative language. These ones are easier because it's like, okay, the derivative in respect to x of v and of u. But I mean, if you're reading dy over du, it can be hard to know. So I find it easier just to remember that chain rule is v dash u dash. So we sub it in, so u dash is 2 cos 2x times v dash, which is 1 on u. So u equals sine 2x, remember that. We can simplify this so that it's 2 cos 2x divided by sine 2x. You may be thinking this can simplify to 2 tan 2x. You would be incorrect. it would be too hot to X. I take this syllabus. If you're a spec student, yeah, you should probably know what that is. If you're not, then don't bother. That's about as simplified as it can get. Cool. Second derivatives. Okay, so we are now going to move on to some applications of derivatives, which is super interesting and can actually make up the can be quite hard too. So this is not a topic to take for granted. Right. So we have a function f of x, f standing for function. Its first derivative is given by f dash x, or the derivative of f in respect to x. Second derivative, we put two dashes, and we can go into the third derivative. It just keeps going. There's no limit to how far we can go. And in fact, as we're going to talk about soon, while the first derivative, if we're talking about displacement, for example, might represent the velocity, the second derivative would therefore represent acceleration. And if we wanted to see the rate of change in the acceleration, we'd find the third derivative. So essentially, a derivative is going to tell us, like the thing it's most doing is telling us about the shape of the graph that came before it. If I've got the second derivative, that's telling me about the shape of the first derivative. What do I mean by shape? I mean, like, is it going up or is it going down, and how fast? Because it's telling me about the gradient. So for example, if the acceleration is like 100, like it's massive, if you put the foot down on the accelerator in the car, yeah, well, it kind of makes sense that that's going to tell us that the velocity graph is going to be going up because we're accelerating. So very predictive. More seconds. There's a couple of key points on a graph, then we are going to get pretty specific. You've heard of stationary points before, most likely. Now, a stationary point is where the graph is stationary. So it literally means, like, how I link it is like, okay, stationary, the velocity is zero, we're not moving. And that's kind of what it is. So this is like, don't be fooled, this isn't the first derivative. This is going to be like the original. So this is before any derivatives. And this would be, and here's a little trick. If we count the number of x-intercepts, that can sometimes tell us what type of graph it is. So one, two, three. Three would be a cubic expression. And therefore, it's got a couple of x-intercepts and it turns around a couple of times. Now, when it's not a quadratic, we don't technically call them turning points. We call them stationary points because sometimes it'll kind of like go up, and then it'll stop, but then it'll go up again. Honestly, I can't remember the last time I saw one, but it happens. It happens. So saying it's a turning point, although it looks like a turning point, like this is obviously a maximum, this is obviously a minimum, isn't absolutely correct. We call them stationary points. Okay? Now, how do we find a stationary point? Now that we know calculus, it's oh so much easier. We don't need to, you know, do anything fancy. Essentially, all we do is find the first derivative. So we take the derivative of the expression and then we let that derivative equal zero. So let's say, for the sake of argument, that this expression is y equals x cubed. And then we find the derivative of x cubed, and that is going to be 3x squared. We then want to find when 3x squared is going to equal zero, because those x values are going to tell us the x values, the stationary points of the original graph, or like the kind of turning points. So we let zero equal 3x squared. We have to very blatantly do that. You need to explicitly know that. And then we solve for x. Obviously, x is just going to be zero. And that is going to give us our stationary point of x equals zero. Now, interestingly here, you'll see that, and then it says, oh, well, the gradient, the slope is about to decrease and the slope is about to increase. Now, this kind of goes back, it's the same concept as like maximums and minimums. So this one here is a maximum. how do I know it's a maximum? Because it comes up to this top point and then it goes down either side. It's an unhappy face. Now, an unhappy face is negative. Therefore, the second derivative isn't going to be zero, it's going to be negative. And then here, the second derivative is going to be positive. Why? Because it's a smiley face. It's a minimum. And you might think, oh, you're down in the dumps, but guess what? It can only get better. It's a big, happy face. And therefore, the second derivative is positive. And that's because the gradient is about to increase. So it basically tells us it's like that split second when you put on the accelerator coming off the line. You're not moving yet, but obviously you're going to be moving and you're going to be moving forwards and not backwards. Okay. Concavity. So it's starting to get a bit technical. Do I need to know this? Is this a load of bollocks? No, you do need to know it, and it is important. You will get quizzed or you'll be given an example, and then they're going to ask you to define the concavity or to find the second derivative or identify whether the stationary points or find the points of inflection, which we'll talk about in a second. So yes, you need to know this. Now, if the second derivative is positive, that means we are going up. If the second derivative is negative, that means we're going down. Now we have special words for this, which we call concave up and concave down. So nothing too fancy. It's just like, is it going up, positive, going up, concave down, negative, going down. And the second derivative is negative. Um, if the second derivative equals zero, this is actually called a point of inflection. Now, a point of inflection is not as easy to see as a stationary point. Stationary point, I mean, it's not rocket science, guys. It looks like a turning point. Obviously, the graph is kind of doing something different there. Now, a point of inflection is interesting because it deals with, so let's define it first mathematically before we move on to visually, because it's potentially easier to see mathematically. And that's because a point of inflection is when the second derivative equals zero. Now, let's remember what I was talking about before. The second derivative actually is talking about the shape of not the original graph, but it's talking about the shape of the first derivative. Okay. Now, the first derivative is a bit more obvious because if the first derivative is positive, it's going up. If the first derivative is negative, it's going down, like the original graph. And here we can see that before the stationary point, it's clearly going up, so the first derivative is positive. Then before that, we can clearly see it's going down, and then it's going up again. Now, inferring the second derivative is a lot harder because the second derivative kind of is a bit more. It's more like seeing a chess game 5 steps in advance. If we look at this, we can see that it's going up pretty fast, yeah? Like it's pretty steep. But then it kind of slows down. It starts to slow down before it hits that stationary point. Now, the key part is that the second derivative, when the second derivative equals zero, is actually going to represent a point of inflection, which is where it starts to slow down because here it's going to be speeding up, speeding up, speeding up, speeding up, and then it starts slowing down. Where would I say it's starting to slow down? Maybe around here would be the point of inflection. But again, I don't know. And this is a pretty lousy graph for that. The other one here, so second, it's going down, going down, going down, less going down, and then it goes up. Because it can't just like suddenly change. It has to be graded because it's predicted by math, which actually means it has to be quite beautifully smooth. Now, I would say that around about here is a point of inflection because as you can see, like it starts off like the downness starts off pretty slow and then it gets really darn steep and then it slows down again as it hits this other stationary point. I would say the middle of those two kind of like, so the middle of the steep part, I guess, would be what would you call it? Would probably be about that here. So kind of like finding a equi equilibrium point in chemistry. Um, and by the way, the 8 notes book that I was thinking of is the complete course notes. And I should know because my name's on a couple of them. I think of them as kind of, they're like textbooks, but they're written by students. So a lot less heavy, and I don't feel like I'm dying when I'm reading it. Like I don't feel insanely bored because it's written by someone who got insanely bored by boring things. Um, so yeah. Anyway, um, cool. Okay. Hopefully you can grasp that. So here are definitions: stationary point and point of inflection. Honestly, high yield. You do need to know that. There's a minimum, there's a maximum, there's a point of inflection. As you can see, it's like the middle of the steep bit, or the point of equilibrium if we're doing titrations in chemistry. All right, modeling motion. So a couple of um, common applications: position, velocity, acceleration. We've already talked about these. So the velocity of something is is the derivative of the displacement. And you're probably thinking, okay, well, what have you written? That's not what you've written. That is actually, yeah, what is written. So we use this weird terminology. XT uh, is essentially displacement. So it'll be like, XT equals t squared or something like that. So how far away it is equals, um, you know, how much time is elapsed squared. So it's something, it's kind of what we're doing here with position, velocity, and acceleration in methods, because in specialists we dive into kind of the relationship between them and with other variables. But methods we just focus on, okay, we have a particle and it's moving and we can map that according to time. So we can plug in different time values and it's going to give us different positions, velocities, and accelerations. Cool. So what we do essentially is to find a velocity, therefore, we differentiate with respect to time. Um, and acceleration, we, you know, differentiate the velocity in respect to that. So you might be given a displacement and you might be asked to find an expression to the acceleration, or you might be asked, okay, here's the displacement, find the acceleration at 10 seconds. You're like, whoa, whoa, whoa. But in reality, that's a really easy question because guess what? You could just have to differentiate it twice, free mark, and then you just have to sub in the time that they've given you and you got 3 marks without, using any kind of, it's probably simple familiar type level. But I suppose some would call it a complex familiar question because they haven't stepped it out in A, B, C. Here's another tip. If you're someone who if you want to like make hard questions for yourself and like you like to challenge yourself, which shout out, that's a good that shout out because shout out to you because that is a good skill to have. Now, what you can do is a lot of textbooks really step out the question in a really almost patronizing way, which is helpful when you're starting, but not when you're bored easily. You can actually cover like A, B, C, D, E, and then let's say that the last part of the question is E. And if you go straight to E, using the information given in the question, usually A, B, C, and D like stepped it out to get to E. So it actually becomes complex, familiar, unfamiliar automatically when you just skip to the last part of the question because you have to kind of piece together what A, B, C, and D is. Not for everyone, but for some people, honestly, that you're better off testing yourself at your level. For others, they need more work with the basics, and that's totally fine. I'm not here to recommend something that works for everyone because I'd be lying. But, um, so, so we can model motion and we can be given the velocity and we can also go on up and down. I will point that out. I know that we've been kind of dancing around integration so far, and we're gonna come to it quite soon because we're nearly at the end of derivatives and shortly we will be moving on to integration and we'll show you how. But integration is the opposite of differentiation. So essentially, if we're given the velocity, I can also find the position by integrating the velocity. This is what we were talking about before, because velocity is the derivative of the position. So how do I go backwards to get to the position again? I integrate because it's the exact opposite. Okay? They're the opposite. That is a foundational logic that your life will be a lot easier once you Let's just understand it. Okay. All right. Let's do an example question. So the position x of the particle after t seconds is given by this function. Xt, so we know we're talking about displacement. Position and displacement is the same thing. Xt, so the displacement across time equals 4 minus 4 cos pi t divided by 4 between 0 and 8. Part A, find the function for the acceleration of the particle. B, find the time at which the particle is not moving. C, find the times at which the particle is not accelerating. So, once again, if we were to cover that, you'd find that part C kind of makes it complex and familiar. If you were to go straight to part C, feel free to do that in your own time, but we are going to move on because the speeding through stuff. You're not supposed to learn everything today. That would be ridiculous, but it's more about kind of reteaching, I guess, refreshing you and giving you a brief introduction. So when the teacher says it in class, you go, that makes sense. And your classmates are like, no, shut up. It does not make sense. You're like, actually, it does. And it is a good feeling. So stop it today because you want the marathon to be better. Train harder so the marathon is not as hard. Cool. So finding the function for the acceleration is going to be two derivatives away because if we differentiate it once, it will give us the velocity and again will give us the acceleration. Not too hard here. The derivative of 4t is just going to be 4. Okay. Actually, no, it was the derivative of 4, wasn't it? The derivative of 4 is just 0. They've explained why here. I think that's unnecessary. Basically, if it doesn't have a t on it, it's going to get absolutely wiped by the derivative. We are just not going to consider it. Minus 4 cos pi t over 4. Derivative of cos is sine. It's negative sign, so the two negatives are going to cancel out. It's actually going to be positive. And then we bring the derivative inside of here to the front, which would be pi over 4. And we bring that to the front, so 4 times pi on 4. 4's cancel out, it's just pi, leaving us with pi sine pi on 4 over t. Now that's the velocity, not the acceleration, so we go again. We could also represent x dash t as vt, and we could represent x dash dash t as at. Oh, right, as you can see on the left. Cool. Next, what we do is repeat this process. So the derivative of sine is positive cos. We bring the pi on 4 to the front. So it's pi on 4 times pi, which becomes pi squared on 4 times cos, keeping the stuff in the brackets the same. So you can just differentiate and integrate grid forever. Like it doesn't reduce to nothing on like power rules, where at some point the derivative is going to be 0 because you've knocked off all the powers. Part B, find the times at which the particle is not moving. This is more interesting. So when is a particle not moving? The particle is not moving when the velocity equals 0. So the velocity is the speed, remember that. So if the speed is 0, it's not moving. So basically we take the expression that we've now got for the velocity and we let that equal 0. So 0 equals pi sine pi on 4t. Now we're going to divide both sides by pi just to get rid of it. Now we get this expression 0 equals sine pi on 4t. Now, to be honest, most of the students that I tutor don't know how to solve this. If they're their calculator, that's kind of what they're used to. They might put it in their calculator, but that might not even work in this context. So this is how I'm going to explain it, and I wish I'd filled out the working out a little bit more, but that's fine because I can just explain it anyway. Um, 0 equals sine pi on 4 over t. We're gonna pretend that that's just like 0 equals sine A or something like that. Now, what I'd like to do is go, okay, well, when does sine something equal 0? Now, remember that in trigonometry, what we've been taught is that cos something equals x and sine something equals y. So on a unit circle, and it's the same I can't draw, when does y equal 0? And the answer is at the two x-intercepts. Okay, so unit circle, two x-intercepts. Okay, what are those? That's when the thing inside of the brackets equals 0. And then when it goes halfway around, what is halfway around? Halfway around is pi. Okay, so, and then we just keep going. So we want to do a couple of laps. So go 0, pi, all the way around again, 2 pi, 3 pi, 4 pi, and so on. Okay, so essentially we have this sequence of 0, pi, 2 pi, 3 pi equals um, equals the thing inside the bracket now, which is pi on 4 times t. Okay, you're probably going to have to watch this part again because it is kind of complicated. Honestly, like it might be something, get your regular tutor or get your teacher who like pull up this part of the slide and get them to just do the working out for you. They might do it slightly differently, but it is worth knowing because Tech Free is an exam, by the way. Anyway, so we currently have that sequence of, okay, when does sine something equal 0, or when does sine pi 4 p equal 0, and that is going to be at 0, pi, 2 pi, 3 pi, 4 pi. So that equals pi on 4t. Now, obviously, we want to get t on the own because we want the time. So we're going to multiply both sides by 4 to get rid of the divide by 4, which is going to turn it into 0, 4 pi, 8 pi, um, 12 pi, and the last one was 16 pi. Now we've got that all equals pi t. We want to get rid of the pi, so we divide both sides by pi, and that's going to cancel out all those annoying little pi's, because remember how it was like um, uh, 4 pi and 8 pi. Those are all going to cancel out, leaving us with 0, 4, 8, 12, 16, 20, blah, blah, blah. They've actually got it wrong here technically. I didn't do this working out. It should be dot, 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 because this sequence is going to go on. Oh, no, I'm actually incorrect. Because they've capped the domain at 0 to 8, we only consider the ones between 0 and 8. So they are right there. I take it back. Though they're, yeah, anyway. If you're keen-eyed, they should have put a greater and lesser than, like the equal to sign there as well. Right, see. Oh, man, I'm going to get a picture for that. Find the time at which the particle is not accelerating. So it is not accelerating when acceleration equals 0. So we literally do the same thing. We sub in equals 0. Maybe have a try using the logic I used before to prove that t equals 6. Remembering the stuff at the front doesn't matter because we just divide that out. It says a 0 here. It's low-key irrelevant. And then just use logic. Go, okay, cos is x. When does x equal 0? X equals 0 at the y-intercept. When do the y-intercepts happen on the unit circle? At pi on 2 and 3 pi on 2. Okay, great. Those are your landmarks. Then you go around and add 2 pi and you do more. Okay, optimization. This is a really fun one. And honestly, you might have done it before, but not necessarily. So a lot of function problems will require you to find the maximum or minimum. Um, sorry, I'm just going to put on my laptop charge. The maximum or minimum value of some kind of function. Now, usually these functions actually can be um, quite complicated and can be quite interesting. Just give me just half a second. Oh, I know. It's clear. And essentially, I know I'm on camera, but you don't need to see. Um, essentially, we use derivatives to find when these optimum situations, like the maximum amount of money that can be made, or something like that, we use derivatives to find this. And the reason is quite simple, because if you were to graph, now working. Oh yeah, cool. If we are um, we're optimizing something. I'm trying to bring it back to something that makes sense to you. Like, let's say that I had an area and I'm trying to find the best shape. I'm trying to find the best area um, with given perimeter. And the answer is probably going to be a square. And we can prove that mathematically. Depending on like the answer is probably a circle, to be honest. But um, we can then map how we change the lengths of the thing. We can map that or graph that of length versus corresponding area. Because if we have a rectangle, it's pretty inefficient. A square is the perfect one. And if we find the derivative tells us the gradient. And when the gradient is zero, that's a stationary point, isn't it? Now, at a stationary point, what do we call them? What is another thing we call them? Turning points. Okay, not as correct, but still how I functionally want you to understand it at this stage. So a turning point is going to be like a minimum or a maximum. Let's say it's a maximum and we want the maximum area. If we can find the stationary points, find out which one is the maximum, that is going to that's give us the answer, and it's fantastic. And then we can use that to like gives us an x value. So we find what x value gives a station point of zero. That's the maximum, and then we work with that to sub it back in to see what that area is into the area formula. So it's not too hard, but you need to recognize it, and it's often always a worded question. Ergo, it can be a little bit more difficult. To be fair. Okay, so then that's what it's called optimization. Now, there is a bit of nuance to that I wanted to mention because we don't know if the minimum or maximum that we found, if it's a stationary point, because the derivative is going to be zero, whether it's a maximum or a minimum. Okay, that makes sense. But we can identify whether it's a minimum or maximum by finding the second derivative. Now, if the second derivative is positive, it's going to be a minimum. Why is that? Because if it's a minimum, remember it looks like this. It's like a happy face. Okay, positive. So if the second derivative is positive, it's a happy face, ergo it is a minimum. If it's a negative second derivative, that means it's an unhappy face, which means that it is going to be negative. Yes. Which means it's going to be a maximum. Yeah, I said that right. Unhappy face, maximum. Cool. Here are a couple of examples, but let's get on to integration because we only have we have um, about 25 minutes left. Cool. This is a fun little graphic that I did keep in because it basically shows that the derivative is the opposite of an integral. So let's say, you know, the derivative of a chicken is an egg. Well, then if we integrate that egg, we then get to a chicken. You know what this kind of really reminds me of? Sine and cos. Because what came for sine or cos, the chicken or the egg? It's so hard to say. All we know is that, you know, if we, you know, have a chicken, it's going to make an egg, which is going to make another chicken. There's definitely that swapping thing that we get with differentiating and integrating sine and cos. Um, okay, that was just a bit of fun. We also call it anti-differentiation. It can be a matter of personal preference. You might have been absolutely tweaking this whole time, going, "What is this guy talking about?" Um, but integration is just how I've been taught, so it doesn't matter. It really doesn't matter. The good thing about math is that it's not English. There tends to be a right answer, um, and the right answer is not whether you use the right grammar. It's about whether you can apply complex skills. No, not that I hate English, um, but some people kind of find comfort in that. Not me, but some people find comfort in that. Um, all right. definite versus indefinite integrals. So this is purely introductory because the way they've restructured the syllabus means that you actually don't really know, you don't get taught what an indefinite integral is. Sorry, what a definite integral is just yet. But I want to keep it in just because textbooks are outdated, resources, because it's such a minor change, won't take this into account. And so you'll hear, oh, how to solve an indefinite integral, and you'll be like, oh, I haven't been taught that. I don't know what that is. In reality, that's literally just how to solve an integral. A definite integral is kind of where we do the integral and then we sub in values and we like minus it. And essentially, why is because a definite integral tells us an area under a curve, which is super crazy to think about. And that's why this is super important math because it was actually used by like all these like cosmic mathematicians. So it's pretty cool. But we're just going to stick with currently you're doing indefinite integrals. I just wanted to introduce that, and it gives you the gradient or the shape of the previous one. Right, constant integration. So whenever we integrate, we are doing the opposite of differentiation. Um, so essentially, it's finding the shape of the gradient. Um, And one key concept is the plus C. Now, this is an interesting point because why is there a plus C? So C stands for constant. And the reason is, let's say that I had like x squared plus 5, and I found the derivative of x squared plus 5 to be 2x. Okay. What if I wanted to go, oh no, now I want to get the original function back. So I integrate x squared. What is the integral of x squared? Sorry, 2x. It's going to be x squared. But where did the plus 5 go? Because I've essentially deleted the plus 5, um, I can't actually get it back. So we have to acknowledge that fact that the constants just get deleted and erased from the memory. There's no control Z of the constants because they're just kind of like dumb constants. We just ignore them. And so we have to put a plus C. And sometimes we can find the plus C with initial conditions. So the integral gives us the shape, but it doesn't tell us the vertical position of the original function. And you will lose marks if you don't put a plus C, I will say that. I actually forgot a plus C on one of my internal exams, and it cost me a whole mark for the year. I nearly got 15 on that assignment. So one of the 3 marks I lost in the year was because I didn't do a plus C. So it happens to, I wouldn't say the best of us, but it happens to all of us. Um, and it's really 3 marks that you can avoid losing by just practicing and being conscientious because just because you forget something like that doesn't mean that you are dumb. It just means you haven't practiced enough. And I'll be honest, I hadn't practiced enough um, either. Okay. So when we have an integral, we can break it down into separate parts. Also, constant coefficient, common to the whole thing can be dragged out the front. We were talking about that before. So essentially, like I can separate out an integral. Like if I had the integral of sine x plus x squared dx, by the way, that dx is in respect to x. And it's actually important to write that in everything because otherwise we don't know what's a constant and we don't know what's a variable that we're actually like integrating for. Seems stupid. Please, please, please just get into the habit of just doing the dx. Just write it. It's too, but otherwise you'll get all of them wrong. And there's been horror stories. It's not unheard of. So please get it right. Anyway, we can separate the integral sine x plus x squared dx into integral of sine x dx plus the integral of x squared dx. Okay, so we just separate them up. The next one is if we can like find a common factor between everything in integrals. So here we can see that everything is divisible by 2. We can bring it to the front. Okay, easy as because it doesn't really affect it. Um, yeah, and then dx just in respect to. Okay, general integration formulae. Here they are. They're the opposite of differentiation. We have power rule. So instead of reducing the power by 1 and multiplying the front by the new power, we increase the power by 1 and divide by the new power. Okay, so it's kind of a bit wacky, isn't it? Um, this is on your formula sheet. So like, please, 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 please practice this until it feels comfortable. And when you forget it, it's on your formula sheet for when you practice it again. I'm just going to focus on the left column for now. The integral of e to the power of x, the derivative of e to the power of x was just e to the power of x. Note that there's a plus c in all of these. The integral of 1 over x is the opposite of the derivative of ln x. Therefore, the integral of 1 over x is going to be ln x plus c. Then the integral of sine x is going to be negative cos x because the derivative of cos x is negative sine x. And then vice versa for the cos x. Okay, pretty easy. Like, this is on your formula sheet one, two, it's the opposite of differentiation. So although it'll take a bit of practice to make it not feel awkward, it's not rocket science. Now, you're probably looking at the stuff on the right, like, okay, but that does look like rocket science. Like, what kind of rubbish is that? Fair enough. And to be fair, I haven't formatted it great. Couldn't work out how to get it up the top in PowerPoint, unfortunately. But it'll make a lot more sense when you write it out. So essentially what I've written is x to the power of f of x. So this is the same terminology and what's the right word? Um, this is the same nomenclature that QCE was using. So if we've got a function up the top there, we bring the derivative out the front. Integration is the exact same. So we still do the integration, but if we've got an f of x or like an ax plus b or whatever, instead of multiplying the whole thing by the a or the f dash x, the derivative of what's in there. So here I would be talking about, okay, if it's x to the power of say 2x, and I'm talking about the 2. Instead of multiplying it out the front, we divide it out the front. Okay, so that's the only difference. So it would be 1 over 2 times x to the power of 2x plus 1 divided by 2x plus 1. Okay. Same with the exponential. So the integral of an exponential is just an exponential. The only difference is we multiply it by 1 over the derivative out the front. Once again, this is going to make a lot more sense when you get rid of the up arrows and you put the divided bys like so that it actually looks like a divide by like it does on the left here. It'll make a lot more sense then. It looks like gibberish now, but once you've and to be honest, here's my 2 cents. Put this on your formula sheet, 100%. Put this on your formula sheet, literally right next to it. Because there's no shame in referring to this because eventually you'll memorize it. But I don't want the danger is for a lot of students that they just skip questions because they go, oh, I don't know how to do that. Or I don't know what formula they used in the answer. Which is why I want you to collate formulas like this on the formula sheet. So it's like training wheels, okay? No one just goes without no training wheels. You know, you have to use the training wheels to get the basics right, and then you take off this training wheel. And sure, it might be scary, but at least you've ridden a bike before, and you're gonna you're gonna push past it. Okay, so you need certain sports at different stages. I'm saying that early on, and practicing just so early on, you got a long way to go. Write these on your formula sheet and refer to these darn things. Have no shame. Okay, same thing with the f of a l logs and thing. We just um, divide by the go essentially one multiply it by 1 over f of x, f dash x. Sorry, I should say. Oh, I know I've written it wrong. There I have. Yeah, I have written that wrong. I will endeavor to fix that on the slides. F dash x here and f dash x here and f dash x here and f dash x here. Sorry, no, f of x here, f of x here, f dash x here, f dash x here. Okay, example. Here's an example of indefinite integral with initial conditions. Here's the question. So find the equation for displacement of a particle, x meters, given the acceleration is 2 meters per second squared. The particle started from rest at 3 meters. Now we know the acceleration and we want to find the displacement. We have to go through velocity first. So um, remember that acceleration is further down than velocity, which is further down in displacement. So we integrate and tick up to velocity, That's going to be a good starting point. So velocity equals the integral of 2 c dt, so in respect to t, because we're talking about time here. Um, so, and then the integral of 2 is t, we raise the power by 1 plus c. Now it started from rest, so we're going to rest means that speed is 0. So we're going to use the fact that at t equals 0, c equals 0, because we want to solve for c. Otherwise, it's going to get too complicated. Solve for c, find c that c equals 0. Therefore, velocity equals 2t. Lovely, big win. Displacement equals the integral of velocity. So now so displacement, velocity, acceleration. We've already ticked up to velocity. We're going to go up one further. So we're going to integrate the velocity to find displacement, once again in respect to t, which is time. Um, so the integral of 2t, we raise the power by 1 and then divide by the new power, remembering that t is to the power of 1. So then divide by 2, which is the new power, x equals t squared plus c. Okay. Now we're going to have to find for what c is. So we go back to the question to hunt for more information, and it starts at 3 meters. So starts, that's when p equals 0, that's the starting position, and um, 3 meters, we're going to presume that that's positive. Usually displacement is like left and right, so negative is left and then positive is right. So if we sub in that x equals 3, that's totally fine. So when t equals 0, this equals 3, and then we get this final expression. Beautiful. And then you might have to apply that. So harder questions might get you to apply that and find certain things. But that's a nice, simple, familiar, I would say. Cool. Okay, let's take a little bit of a brain break. We've got about 27 slides to go. In about 10, 15 minutes. Sounds scary, but the rest is pretty easy. Discrete random variables is like the easiest of the probabilities. It's not that hard. This was previously in Unit 4, but they moved it to Unit 3. To be honest, I'm not quite sure. Um, but most of it is a little bit beginner. Like the probability seems strange, and if you're not paying attention in class, you'll listen in randomly and you'll be like, okay, I don't know the first thing about that. What even is that? So it's an abstract concept, but the question can be quite easy. Like you've just got to pick what type of probability it is. That'll make sense at the end of Unit 4. You pick which type it is and then go, okay, I'm just going to use a formula from there or use my calculator with that function. It's not that hard. It's definitely easier than hard integration or hard logs, of which you can get a hard question. Check out the last question in 2023, paper 2. I remember the only one I know who got that question right. It was very difficult. I won't give away how you solved it. But I'm sure you'll see it in your studies, especially as you get up to externals. Don't do it yet. Um, okay, so if something is discrete, it's not continuous, and it is something real. Like I have one water bottle. Number of water bottles is discrete. Number of lamps is discrete. Number of laptops is discrete. Number of people is discrete. Um, Whereas something continuous would be like time. And you might go, oh no, but 2 seconds just passed. Oh, you said you have 12 minutes left. Yeah, but it's not exactly 12 minutes, is it? Because it's 12 minutes, 12 seconds, 0.01 milliseconds, and you just keep going. And the thing about continuous stuff is it goes past the point where it can be measured. So we go down so far that we can't even measure it anymore. And that's why you actually have a perfectly unique height, because you can never go specific enough that you have the exact same height as someone. Okay? Yes, for observable purposes, you have the same height, but in actuality, you do not. And we can't even measure it to go down that far. We never will, because it's always going to go further. Okay, so here's some more definitional stuff. So discrete random variables. Um, essentially they have different values of x. So this is what it's saying. So p means probability. Xi is just like a specific value of x. Um, and the probabilities must satisfy. Essentially, what this means, I'll explain it in English for you. All the probabilities must be between 0 and 1. Okay, sure. The probability can't be less than 0 or greater than 100%. And the sum of all the probabilities must be 1. All the probabilities have to add up to 100%. Makes sense. That's a pretty fair assumption. That's not some strange assumption. That is the probability that we're dealing with for pretty much all of it. Um, cool. When probabilities are not known theoretically, we can estimate them. So if I roll a dice and black comes up 5 times out of 10, I can kind of assume that the frequency is about 0.5. So the frequency or the relative frequency is about approximate of true probability. And this becomes more true the more we do it. If you simulate something a million times, it's probably going to be pretty accurate because the outliers have kind of balanced each other out. And we've had enough middle results that you can't be swayed. Okay, uniform versus non-uniform probability distribution. Okay, uniform. All outcomes are equally likely. So, um, what does this kind of mean? Uniform means all the same. Therefore, if something is uniform, all of the probabilities are going to be exactly the same. So, a die with 6 sides, um, where obviously it's 1 in 6 for all of them. It's not necessarily going to be exactly 1 in 6, but we can kind of assume that. Non-uniform is more likely where the probability of something happening is going to be changing and hard to measure, but we always do our best. Okay. Bernoulli sequence. So a Bernoulli sequence of repeated trials is kind of an extension of binomial probability. And we will talk about this a fair bit. So Bernoulli sequence is quite specific. So we have repeated trials, and one thing is success and one thing is failure. So importantly, there can only be a success or failure. Now you might think, oh, that's pretty specific. When are there ever going to be two outcomes? What about rolling a dice? Well, guess what? What if I wanted to roll a 6? Rolling a 6 would be a success. Not rolling a 6 would be a failure. So we can kind of split it up into complementary events. Okay. Now, the other thing that is important in Bernoulli sequence is that the probability for each trial is constant and it's all like independent events. So if you remember those weird questions from like year 8, where it's like, okay, we have balls in a bag and there's like 2 red and 1 blue, and then we take out, okay. And then there's like probability trees because we don't replace. We're going to assume replacement. We're going to assume that trials are independent events, that what one happens doesn't affect the other. Obviously, this is like impractical in a real world, and sometimes you get to justify why. Okay. We have a number of n trials, and this is the binomial random variable. And it has a probability distribution. So, like the expected number, and kind of like it usually follows some kind of bell curve where, depending on the probability, if the probability of success is really high, then we're probably going to have more successful outcomes. Okay. It's not rocket science. Now, I'm permutation combination specialist. You might know that. Um, but essentially, we have this formula. It looks scary, but guess what? It's in your formula sheet. Um, and it basically tells us um, the probability of getting a certain number of outcomes. So the probability that x equals x, that we get a certain number of successful outcomes, x being the number of successful outcomes, p being the probability of success, n being the number of trials. Okay, and we just sub that in. Now you see this bracket here is actually quite confusing. So this is a combinatorics, so a combination. You can put this into your calculator, that's fine. Just look up how to do it on yours. But the other way is to do Pascal's triangle. We don't have enough time to do Pascal's triangle today. I'll try and remember to do it for the next one. But I think I might do it in the end of your review, or I might have done it in a I'm not sure. Don't quote. If you Google Pascal's triangle, it'll kind of make it clear. But essentially, the numbers go down and then the x's go across. The n goes down, x goes across, and then you just see what the position is, and then it tells you. So essentially, this bracket thing is going to give us a specific number. We're going to make this all work. Okay. Can use a calculator to calculate that using a combination. Um, it sounds a bit complicated. It's really not. It's just something to give you a number that makes the math work. I'm not going to show you this factorials because that's just too specialisty. Okay. Example, find the probability that when a fair six-sided die rolls six times, there is one three, two fives, and five threes. There's the calculation. Honestly, I'm not going to go into it because you sub it in, right? Sub it into the formula and work it out. The only thing is the combination, which is difficult. Okay, technology. And we're going to focus a lot on technology throughout this probability section. Why? Because most of your tech active papers are going to be probability, honestly. So most of them, they're pretty good. Honestly, the tech active exam can be really easy if you know how to use your calculator. Um, but we're going to go over a lot of them. Okay, so binomial probability. Um, in the T and SPY calculator. This is the one that I had. You go probability, distributions, binomial PDF, which is probability density function, and you put in the number of trials, the probability of success, and the X value. So the number of successes, so 3 out of 7 that you're interested in. And it tells you that's not more than 3 out of 7 or less than 3 out of 7. That's exactly 3 out of 7. Okay? You do know that. Okay. The next one is going to be um, for the Casio, so run matrix statistics, distributions, binomial, BPD, and then you put in the same things. I'm going to skip through these because in reality, you're going to have to refer back to these to see them. If it's in a range, so if we're trying to find it um, between like x is greater than 4 or less than 8, where it's not just the probability that there's 4 successes, we can either like individually add up the probability of if x is greater than 4 and x is less than 4, then we go, okay, what's the probability that x is 0, x is 1, x is 2, x is 3, x is 4. Can be annoying, or you can use your calculator. So by using the CDF, so the cumulative distribution function, um, and we go upper bound and lower bound once again, number of trials and probability of success, it's way easier. Run matrix statistics, it's the same thing in the Casio. You just have to use those things. All right, conditional probability. This one's not on your formula sheet, but the probability of getting A given and we've already got B. This can be some like complex extensions equals the probability of A and B divided by the probability of B. How I think of this is we've already got the probability of B, so we get the probability of both A and B. Then we divide out the probability of B because B's already happened, because the probability of A given that B's already happened. Okay, so example is a 90% probability that any given person is right-handed. Classroom 26, the probability that there are 20 right-handed students. And there's the calculation. No, that one it wasn't on your formula sheet. It's like an A-level extension. You wouldn't get asked it usually, but I anticipate that they'll probably ask it on an external this year or the next. I do think it will happen. To make probability predictions about a binomial distribution, we can determine some important statistics. So EX is the mu, which is the mean, which is the expected value, which is just the number times the probability of success, the variance, and remember that um, the standard deviation, which is probably something you've heard before, is just the square root of variance. So something might ask for the standard deviation, you actually have to find the variance first, and then square root it. Honestly, write that down. I don't know why I didn't write it. Please write that down. Square root of variance equals standard deviation. You have to memorize it. And then we just find it using that. Let's get using numbers and probability. So you can go through. Honestly, I'd probably have a practice of these. It would be worthwhile. Here are some hard ones. So finding like how many trials you need to conduct to make sure there'll be like a certain number or a range of desirable outcomes. Um, Given that there's a distribution with a probability of say 0.35, and then we want to have at least one success, um, like with a certainty of about 95%, because it's never 100. So obviously, like if we only do one trial, the probability of getting one success is 0.35. So eventually it gets very big. Now, to do this is quite hard. So, the logic we need to do is we need to set up something like this and then we can work it out. So, we need the probability that x is greater or equal to 1 to be greater or equal to 0.95. Some students will find this really, really frustrating. If that is you, what I would do is just go, okay, I'm just going to put an equal sign here. And what you'll find is you'll work it out. Like it's an equal sign, you can substitute in here, pretend it's an equal sign. Now what we need to do is probability of x being greater or equal to 1, assuming this is tech active, this isn't very helpful, tech free, this isn't very helpful. So we can write the probability that x is greater or equal to 1, we use the complementary event. It's like the opposite thing. So if x is greater than 1, what's the opposite of x being greater than 1? The probability of x not being greater than 1, which is if x is 0, because you can't go any lower than 0. So we do the complementary event, which means we like find 1 minus that. Now we can sub probability of x equals 0 in. We put that into the formula and it gives us 0.65. We then minus 1 from both sides, divide out the -1. Now we put it in logs to solve for n. We find that n is this and put in the calculator there. Thus, there must be at least 7 trials. That's complex, I'm familiar. That is really hard. Worth doing lots of practice for, therefore. And then this is largely the same, but we want 2, so we just have to step it out a little bit more. Um, this one is actually not solvable algebraically. You can use like, numerical nsolve in what's it called? In the Teams file. It's also called numerical solve. So whatever calculator you have, just look up numerical solve. Put this in with an equal sign, and then it'll solve for n for you. It's so useful. Love it. This is how you do nsolve here. Passio. I'll leave that in there. A couple of probability language things. At most means no more than, ergo it is less or equal to. At least means no less than, meaning greater or equal to. Inclusive means includes the endpoints. So we're using equal then sign. So if it was between 1 and 4, but it was inclusive, that means it includes 1 and 4. So just a couple of terminology things that kind of make sense. You probably figure it out. A couple of tips, considering we're at time. If you want to have a study plan, don't obsess with your study plan. It's all about time in the game. Have self-confidence, have belief, remember what you're doing it for. Maybe you're just doing it to keep pathways open. Maybe you've got your heart set on maybe being a doctor or going to space. And it's important to remember that. And like you're going to hear lots of people who don't know what they're doing, and it's important not to get dragged down by others who kind of like try and drag you down because they haven't really picked something yet, which is totally fine. And they might go on to do what you're doing. Who knows? But it's important to have self-direction and to have conviction because you can always change in the future. And honestly, you just got to start doing something. Getting good habits early. Um, Procrastinate, but don't procrastinate too hard. I'm not going to say don't procrastinate, but um, if you shoot yourself in the foot and leave everything for the last week, external, you don't procrastinate. It has to be a month to study. But we won't talk about them. Work hard on your IAs. They're worth half your grade. And make sure you talk to your teachers because they grade you at the end of the day. External, absolute spam perusal. I do the exams backwards for math because the hardest questions I do first while I got the most mental energy. And I find that then when I get to the easy questions that are like muscle memory, it's just simply easier. Okay. Um, Well, thank you very much for watching. I know 2 hours is hard to present, and it's also hard for you to listen to, especially if you're going to listen to. I've listened to lots of lectures, and I'm zoned out thinking. So if you got, maybe 10% of that, you are 10% ahead of your classmates. So be happy. Make sure you follow ATON Notes on our socials to get more free stuff, and see what resources you can use. And if are in need of a tutor, tutors, I'm looking for more students. Other tutors can take on more students. So make sure you reach out. You literally just search Shoot Max online, and that'll get you where you need to go. Okay, thank you. Bye. Best of luck with your studies.